So today we're very happy to have Erschler speaking about Poisson boundary, Liouville property, and asymptotic geometry of linear loops.
Thank you, and it's a great pleasure for me to speak here. We will speak about harmonic functions on groups. So we start with a group, which is usually will be assumed to be finitely generated. We take some probability measure mu. We take a function from G, R, in the say it's mu harmonic. If for any point the value of the function in this point is the average of the value in its neighbors H, mu of H. This means harmonic. This is just a discrete analog of usual harmonic functions. And I will say a little bit later about more how different discrete concepts and non-discrete concepts, but it's really something very similar to usual harmonic functions. And one of the main questions I want to discuss today. So we want to know, we have a group, we have a measure, we want to know when do we have bounded harmonic functions? Function, and we want that this function is bounded between the constants. No, I'm not assuming that. I will comment on that. So it's a very important case, the most important case for us indeed when mu is symmetric, but the notion makes sense not only for symmetric measures, and today we'll speak both about symmetric and non-symmetric ones. So we take a measure and we want to know. So we want to know, does G mu admit bounded harmonic functions, right? Here, the most classical case was just a abelian group. Let's start with a abelian group. Here, first results goes back to at least to the 30s of the 20th century. So it's 1932. He took just measure which is equidistributed at the measure, the standard measure. And he has shown no bounded functions here. And in fact, for abelian groups, his assumption on the measure wasn't important. So here, a very classical result now. So for abelian group, you should be abelian.
Sorry, what is the name there? I can't read it.
Capulade.
Thank you.
If G is abelian, it's really well known that no harmonic functions. Yeah, maybe I give the name. So this property, if a space does not admit a bounded harmonic function, it's called Liouville property. So it's well known so that on a abelian group, we can't have bounded harmonic functions. So, and the person who proved it's Blackwell, somehow the history sometimes does not really attribute properties to the person that proved them. So this property for abelian groups and for all our groups is nowadays very often called Jacquet-Denis property. But so Blackwell, it was 1955, and several years after Blackwell, if I'm not mistaken, maybe 60, it was a paper of Jacquet and Denis who on locally compact abelian groups have proven the same property. And somehow everybody cites their name and not Blackwell's. But at least for abelian, we know never we have this property.
Is the measure normalized?
It's probability, it's mentioned, it's probability measurement.
So uniform, what does it mean on CB?
Uniform has the same value, so uniform and generators. So Capolati, he was considering that we have D generators and the inverses right on ZD, and uniform meaning so just you put 1 over 2D.
Nearest neighbor. Just nearest neighbors.
Yes, so it's the nearest neighbor, right? So to each neighbor you go with the same probability if you consider the random walk, but for the measure it's like this. But for abelian it's like this. And moreover, not only for abelian, so soon one realized that for nilpotent groups it's also the case. Potent groups. First, it's Dynkin-Malyutov, and soon, more generally, not only for bounded but for positive harmonic functions, Margulis. Harmonic functions, Margulis. Have proven on nilpotent groups you can't have any interesting functions, and actually what Margulis has proven, he has proven more. So he has proven if we have a central element in our group, so we have our group G as something in the center, then C acts trivially on harmonic functions. Trivially at the boundary. So I didn't define the boundary yet, but harmonic functions. So far, that measure is non-degenerate. So far, that support of the measure generates G as a semigroup. It's the case, but if you speak only about it is true for any countable group, but if you're mostly interested in finally generated groups, the groups you can obtain by taking sample extension, it's exactly nilpotent groups, and it's also known passing to finite index subgroup doesn't change this property. So at least for virtually nilpotent, we know very good. We always have Liouville property. What happens next? Yeah, maybe I say first about some groups where we certainly do not have this property, and we do have many harmonic functions. So also in the early 60s, Dynkin-Malyutov first descriptions of all harmonic functions for some non-abelian groups. So if you have, let's start with a free group.
Is it possible to pull the board down a little so we can see the?
Yes, thank you.
Thank you.
On the contrary, if you take a free group, again, we can start with nearest neighbor. The Kelly graph of a free group looks like a tree, right? So, and then harmonic then means at any point, the value is equal to the value for the points of the boundary of a tree. And then in these examples, we don't have Liouville property. What is the way to see it? So you can look on geometric boundary of the tree, right? So somewhere geometric boundary. You can put some measure on the boundary, and you can look on the probability. You can now we can see. Let's say something about random walk. So this notion about Liouville property is very, very much related to random walks on our group, right? So we have an element. So what is random walk? So we have our measure. So we consider the following random walk. So we stay somewhere in the group, and each time to pass from xi to xi plus 1, so xi plus 1 is equal to xi times something size h, and with probability mu of h, right? This is a random walk on a group. And Liouville property and very much related to properties of random walks. And one can describe, actually, in these three examples, one can describe also some harmonic functions without referring to random walks. But I wanted to even easier way to say it if you consider a random walks, right? So what happens with your random walk? So we have a random walk. So we walk and walk on our graph. And something basic and important to know about random walks could be recurrent or transient, right? Even among abelian groups, you probably know, right? Z2 simple random walk is recurrent, meaning with probability 1, we return to the origin. In dimension 3 and higher, it is transient. In fact, it's for general groups, it was less obvious, and it's a result of Varopoulos. If you have a finitely generated group, the only recurrent groups that you can have is only Z, Z2, and finite extension of Z and Z2. And all known proofs use polynomial growth theorem, so there is no very, very easy elementary proof in general, but at least we know very good for many years. For groups, we can answer the question when we have something recurrent and when we have something transient. Now, returning to the free group and to the tree. At the random walk on this regular tree, it is easy to see that it is transient. So why? So we just walk, right? So each time, with probability, let's say 3/4, we increase the length, and with probability 1/4, we go closer to the origin. That's clear then if you look on the length, right, on an array, you have a random walk which shifts to the right, and then clearly with probability 1, we will never return to 0 after some point. If so, one can take a heating measure on this geometric boundary, and we can consider the function which we start with some random walk, and we consider some subset, for example, on the boundary, and we consider the probability to hit this subset starting from some point. This is clearly a harmonic function and bounded, just take values between 0 and 1, right? So in some situations, like here on a free group, so we can't have Liouville property. And in general, the following is known, right? So if G is non-amenable, a free group is an example of an amenable group, right? And then whatever measure you take, measure mu, not necessarily nearest neighbor, you only assume that support of mu generates G as a group. In some results I mentioned it was embedded as a semi-group, but here just in a very basic sense, just if the support of the measure generates the group, then we always, then there exist bounded harmonic functions. This is some basic observation to Asymptotic and Furstenberg. Asymptotic was the first, to my knowledge, the first one to prove it. But he wrote a paper in French, and many cite Furstenberg, which was several years later instead. But anyway, nowadays it's really something very basic. If we are in a non-abelian situation, the boundary is always non-trivial. We always have non-trivial bounded harmonic functions. On the other hand, something else which is known, that there is a strong relation to the growth of the space. So when we have a group, we consider the growth functions. function, BFN growth function. Looking on the size of the ball in our calligraph, so just growth function by definition the number of elements of length, word length at most, and so when I say word length, just we take an element of a group, write it as a product of generators, and look on the shortest way to write. This is the word length, right? And so this is the growth function, and something. Maybe I start by mentioning result of Abyss in 1972. He proved the following, that if the V of n is sub-exponential, and Abyss considered simple random walk of G, simple random walk meaning symmetric nearest neighbor on the random walk on G, then we always have Liouville property.
Do you define sub-exponential? It means at most exponential or better than exponential?
No, the growth. So we consider finitely. Thank you for the question. Finitely generated group. So we have a finite number of generators, right? We look on words that can be written as a product of n generators. So we never can have more than this number of generators to the power of n elements. So the growth clearly never greater than exponential. Sometimes, like in this example of ZD, it's polynomial, right? So in ZD, the growth is approximately n to the d. Sometimes it's for the free group, it's exponential, right? So for this tree, regular tree, the growth is exponential. So, but the growth can be polynomial, can be exponential, or it can be intermediate, something between exponential and polynomial. And so Abyss, he then.
So he's just assuming little o of exponential.
Yes. So if the growth is exponential, he has observed, then we always have Liouville property for nearest neighbor random walks. And at this point, he defined a notion which will be very important for us today. He defined entropy of random walks on a group. He said like this, so we have our measure mu, we take nth convolution of mu, so n convolution is clearly something that describes the distribution of our position after we make n steps of the random walk. So he considered the entropy, meaning, well, entropy meaning sum minus log mu of G, so far usual entropy of a probability distribution, but and sorry,
You convolved n times, not mu.
no, this is mu. So
The entropy of mu convolved.
this is mu. Something else.
You wrote the entropy of mu, right?
Derivative of random walk. G mu.
I think you just want to put like a star n on the right side.
The right-hand side.
Sorry, just a second. Maybe I finished the definition.
Oh, there we go.
So Abyss suggested to do the following. We take n convolution of our measure, which defines our random walk. We take the entropy and we divide by n. So it's easy to see this is something sub-additive. And then if you take maybe I say expectation. So we take expectation of the entropy of nth convolution divided by n. It's clearly there exists a limit, a constant h. Yes.
I think instead of mu g, you want mu star energy.
Yes.
Yeah.
Yes, thank you very much, Anna. No, yeah, absolutely. Thank you very much. So we take the distribution after n step, take the entropy of this distribution divided by n. It's clearly there exists a limit, and this number is the entropy of the random walk. And what Abyss has proved, if h is, so he assumed that support is finite, support mu is finite. And he proved if H is equal to 0, then we have Liouville property. All bounded harmonic functions are finite.
The sum is over G. All group.
Yes, it's a sum over G. Maybe I wrote expectation. It's the sum. Thank you. I was sorry. I was inaccurate with notation. So it's sum over G and G. Is it better? Maybe now. So we take indeed we consider all elements of G. We take the sum over elements of G of log mu n of G multiplied by mu of G. N divided by n, and we take the limit. So I wrote expectation because it's the same as to say we take our position xn, and we take expectation of entropy at this nth position, we divide it by n, and there is a limit. We call it entropy of the random walk. So it turned out that the assumption that the support is finite in the theorem of ideas is not essential. And moreover, it's if and only if statement. So what is not a theorem that starts with ideas, but also in the other direction and more general assumptions due to Rosenblatt and Kaimanovich and Erschler. Erschler is that under the assumption that entropy of mu is finite, and this is essential. So far as entropy is defined, in particular for this is the case for finitely supported measures, obviously, then H equal to 0 is equivalent to the fact that G mu is Liouville. But in particular, yes. So if the growth is sub-exponential, clearly entropy of any distribution is not greater than the log of the cardinality of its support. So if the growth is sub-exponential, then it's clearly entropy is 0, and this is how the proof worked for this. And so for many measures under this Mant assumption, now we knew not only for virtually important, we knew for all sub-exponential growing groups. At that time, it was not known. Is it essential that we assume for this corollary that entropy is finite or not? So it took some time to understand. Now we know good as. So groups of intermediate growth can admit measures, but then infinite entropy measures with non-trivial boundary, with bounded harmonic functions, and maybe I will speak more about more usual groups today. So this we knew, but what happens in exponential growth? So in exponential growth, a priori, there are no obvious estimates for the entropy.
But could you just give us a hint how you proved this statement?
The statement about entropy. Well, you take the convolutions of the measures and you take shifted convolutions. You take shifted convolutions and you look the difference in L1 between mu n and h mu n. One can see that the entropy is defined by the asymptotics of the L1 difference between the convolutions. So in particular, if entropy is 0, meaning the difference are small. But now take a harmonic function. If the function is harmonic with respect to mu, clearly it is harmonic with respect to convolutions of measures, right? Just writing the same formula n times, you see, if harmonic with respect to mu, then we respect the convolution. Then after we know that L1 difference between mu n and h mu n is small, you see the difference is small, and we see that we can't have a bounded one then, right? So this is how it goes this direction, but in fact it goes in both directions. It's really if and only if, right? So So, and the first question I want to discuss, now we have a group of exponential growth. Yes, if the group is non-amenable, we always have harmonic function, but what if the group is amenable? Here, both situations can happen. Indeed, there are vast classes of amenable groups where the boundary is trivial, and vast classes where it's not trivial. Before I explain that, maybe I make some comment about different definitions of the boundaries, because I mentioned boundary, but that is only speaking about harmonic functions. So there are many ways to define something which is called Poisson boundary of a random walk on a group. One of the equivalent definition is indeed in terms of harmonic functions. So to say we described the boundary completely is the same as to say we described all bounded harmonic functions. In particular, to say the boundary is trivial is the same to say we have no bounded harmonic functions. But there are many other equivalent definitions. So one of them is like this. So we consider the trajectory for random walk and consider the time shift on the trajectories. So with the trajectory x1, x2, x3, we consider
There's subtleties between bounded and positive.
Pardon?
Bounded harmonic functions and bounded on one side. Or that, positive harmonic function.
Positive harmonic function, thank you for question, sir. Positive harmonic function is a much less strong condition. In some situations, as I mentioned, in the result of Margulis, for nilpotent groups, you don't see the difference because we don't have even positive ones. But for in other situations, it's really very different. For exponential groups, strange enough, it was remained open until several years ago, but now it's a result of Kozma and Yadin. If you have exponential groups, always we have some positive harmonic function at least, right? And for us today, mainly we speak about bonds. And for bounded, if you take exponential growth, there are many situations where maybe we don't have at all, and sometimes we have. All right. So, but just wanted to comment to comment on the definition of the boundary. We take space of trajectories and we take the time shift x1, x2, x3, and so on goes to x2, x3, and so on. Right? And the boundary is trivial. So Poisson boundary, even before we say it's trivial, Poisson boundary, one of the equivalent way to describe it, it is a space of ergodic components of this shift. So in particular, the boundary is trivial, even only if the time shift is ergodic. And this is the question I'm discussing today. We have a group, we have many simple random walk or other random walk, and we want to understand, is this shift ergodic? And maybe you know, in dynamical system in general, sometimes even some basic models, it could be profound and difficult to understand whether we are in ergodic situation or not. And today we speak about these questions for random walks on groups. But
What's the measure? To be ergodic, you have to have a measure.
on the space, so on infinite trajectories, there is a natural measure, right? So on each increment, there is a measure mu, right? On each step, we have measure mu. Then on the space of infinite trajectories, not only for many reasons, right? We consider the measure on the infinite trajectories and so, and by definition, Poisson boundary, I don't want to give details of definition, but Poisson boundary is a probability space with measure. So Poisson boundary is not a topological space, it's a space with measure. And we want to understand it. And the duration of the talk is what, 50 minutes or 1 hour?
The whole thing's an hour, including questions.
Okay. Now I want to explain groups of exponential growth that can have trivial or non-trivial boundary. But maybe I give one more example commenting on the definition of the entropy definition of Abes. He was the first to define this notion, but there was some precursor. Just 10 years before Abes, in 1962, there was a paper of Garcia who defined something which is called now Garcia entropy and the subject of intensive research. Garcia didn't speak about groups, but he spoke about Bernoulli convolutions. Something that was studied before by Windner and Erdős in the 30s of the 20th century. And so he did like this. He took a number lambda, he took the sum plus minus 1, lambda to the e, to I, and just he wanted to know what happens for such. So just with probability 1/2, you take plus 1 or minus 1, and he wanted to know what is the distribution there, right? And he considered the entropy. Just he takes this sum up to nth, let's say, and he considered the entropy. And I will explain in a moment. Actually, this entropy can be interpreted as entropy on a certain group, and so it was just in the future when realized it's really a particular case of Abbe's entropy, and it seems that the work of Abbe's that inspired Erschler actually in his first works on entropy, and the corresponding group would be a solvable group of step 2. But before saying that, maybe I say a few words.
Just one question.
Yes.
So this measure here, is it meant to be absolutely continuous with respect to the value?
So here we speak about discrete measures, right, on the group. So yes, no, there is a question about how the limiting measure is absolutely continuous or singular. And so it's either singular or absolute continuous. This was the reason why Garcia was interested in that. Now, our defining measure so far is a discrete measure.
Lambda is greater or equal to 1, I guess. Lambda is bigger than 1.
Lambda is bigger than 1.
Or rather,
Otherwise, I can answer it.
thank you.
Lambda, and okay, so this defines a measure, and then you have to define an entropy.
Yeah, just Garcia considered the entropy of the distribution of the sum up to n. N was starting, and notice that there is
Sorry, yes, okay.
and notice that there is a really relation with number theoretical properties of lambda and how this entropy behaves.
Okay.
But I don't know if I have to explain, but I try to explain maybe so why this entropy is some entropy of on some solvable group. But maybe I mentioned so that there are many examples. So if growth exponential, there are many examples where the boundary could be non-trivial. So there are groups which are non-Liouville, and there are groups that are Liouville. Groups which are Liouville. Non-Liouville we have seen already in non-amenable cases, but also there are many amenable groups that are non-Liouville, and there are many groups that are Liouville. And now, so speaking about boundary, there are many questions we ask. Firstly, we ask, is it trivial or not? Then we ask how group acts on the boundary, because group clearly acts on harmonic function, just multiplying the argument on the left by an element. We ask how it's related to geometry. Can we describe completely the boundary? And we progressed in last decades in understanding this question in various classes of groups. But today I speak simply trivial, non-trivial. And it turns out, even in some very classical situation of linear groups, so now we start thinking about linear groups, right? Linear groups. Take a finitely generated subgroup in a linear group, and we want to, so...
Sorry, you didn't say what Garcia did.
He defined the entropy.
That's it.
But
Computed?
Yes, he estimates entropy and noted that for Poisson numbers, it's strictly smaller than an obvious guess of the entropy, and this is related to the. I don't want too much to detail to explain the equation of the limiting distribution and dimensional limiting distribution. There are some recent works like of Hoffman, for example, and understanding something, but still many questions still open, right, about the limiting distribution. But here I wanted to make this comment just the definition of the entropy appeared in this work of Garcia, and it turned out to be a particular case of obvious definition for random box on a group, and the corresponding group is actually a linear group. And now I want to speak about linear groups. So we consider a group of matrices. Just we could take D times D matrices over some field. And we want to understand, is boundary trivial or not? So for linear groups, there is this alternative, right? So either the group contains a free subgroup, in this case it's non-amenable, and now we know it's a very general observation, the boundary is non-trivial, or it is virtually solvable. So for the moment, I want to speak about virtually solvable linear groups. And it turns out that even in this very basic definition, we don't know yet completely when the boundary is trivial or not. And before stating some of the results, maybe I give some examples what kind of groups we are interested in, right? So what classes of groups we understood before? There are, for example, polycyclic groups. Well, first we mentioned nilpotent groups. Nilpotent groups are basically upper triangular groups with one on diagonal, right? Intertriangular diagonal, these are nilpotent groups, right? On nilpotent groups, we said the boundary at least is always trivial, right? Polycyclic groups is the same as to say we take groups with integer coefficients, right? So we take something like, for example, I don't know, polycyclic 2, 1, 2, take some matrix with determinant 1, like this, maybe 0, 0. And take extension of Z2 by this matrix. This is an example, very basic example of polycyclic group, but I want to write it in a linear form to make a connection to the results I want to explain. And you take, I don't know, 0. We took 1 here, 1, 0, 0, 1, just to have a copy of that. It's hard. 0, 0, 0, 0, 0. We take 0, 1, 1. This is just example of polycyclic group. You take three matrices like this, right? So determinant is 1, so the inverse matrix is also has integer coefficients, so it's clear it's some group with integer coefficients. This is a polycyclic group, right? So it's a very old result of Kaimanovich. For example, if you have a polycyclic group for symmetric measures with finite support, the boundary is trivial. But now, also it was known for measures with, maybe I mentioned, so for polycyclic, this for, I don't want to write exact condition on the measure, but it is for simple random walk in the polycyclic, then result of Kaimanovich, boundary is trivial. It's trivial, so the Liouville expression is trivial. Or we can, let's take now not integer coefficients, which is the same as to say polycyclic, let's take rational coefficients. This is a result of Porphyria for 2 by 2 matrix in linear case by Shapira. The same conclusions for polycyclic. But for some other solvable linear groups, one knows very good that the boundary could be non-trivial. So maybe I mentioned the example like this of a Reeve product. Take the matrices of the following form. One matrix is 1, 1, 0, 1, just 2 by 2 matrices. And the other one, 1, xi, 0, 1, and I from 1 to some number d. If you take such matrices, the group they generate is d-dimensional Reeve product. With z, if the coefficients are integer, or with z, pz, if you take over z, pz, this is a Reeve product. And this was an example, a starting point for the theory of Poisson boundaries, Kaimanovich and Erschler. If D is greater than 3, the group is solvable, amenable, but the boundary is non-trivial. if D is equal 1 or 2, the boundary is trivial. But now I want to formulate, so for many classes of groups, linear groups, we knew what happens, but in general is remained unsolved. And I have what, 5 minutes? 5 minutes? Yeah. Maybe I have that. So first I want to explain my result with George Frisch. Take D by D matrices over some field K. Our first result reduces the general D by D case to 2 by 2 matrices. And say the following. We have D by D matrices. We take I and G between 1 and D. Take I and J here. And we take position I position, J position, and IJ position here. Inside our matrices, for each pair of I and J, we look on 4 numbers corresponding to where coordinates are IJ, right? And we do the following. We can, we have some subgroup of linear groups, and we associate some group of 2 by 2 matrices. Just here on diagonal, we write the same numbers which we had in our group. So if we have here MII, here we have MJJ, we write them here MII, MJJ. Now here we always write 0, so 0, 0. And then we look, we define the notion when AJ, when the following J is.
You're going over all the elements of your subgroup, right?
But over all elements,
all
yes.
elements in the subgroup, and you're defining the 2 by 2 matrix.
Thank you. Yes, we start off looking on all elements in our group, which is subgroup in linear group, and we define some subgroup of 2 by 2 matrices. So we look on the pairs. We write some number here, some number here. If for some matrix in our subgroup we have these elements, and here we put 0, 0, and we say now some pairs of indices would be valid and some not. We define what means valid. We say valid if the following also. If in our matrices, so this is basically about upper triangle matrices, right? The solvable group is upper triangularizable. So here we have 0, here we have, if we have somewhere in our position IJ, we have something, I write star, something non-zero. And then if we have 0, 0, 0, 0, 0, 0 in this triangle, and here it's 1, 1, 1, 1. If we have at least one element of this form, we say this pair of indices is valid. And if the pair of indices is valid, we consider this element 1, 1, 0, 1. No matter what element we had here, maybe it's not 1, it's something, maybe there are several very different elements, but for us, we only care if there exists at least 1. We say 1, 1, 0, 1, and like this. So this matrix we call block, this non-abelian block. So we take our group and we say, our random walk, our measure is Liouville. Even only if associated measure on this block is, for all blocks is Liouville. So this completely reduces general case for 2 by 2 groups.
Sorry, you also get, you only get upper triangular, you can get a lower triangular.
No, here I write upper.
Now, you're taking now the group generated by these guys that you form? What's your 2 by 2 matrix?
One is 1, 1, 0, 1. The other one is diagonal, just 2 numbers on diagonal and 0, 0.
And you take the group generated.
Generated by the
That will be upper triangle.
upper triangle.
Okay.
And for each I and J, you do this.
For each I and J, which is valid. Sometimes if the pi is not valid, if there are no elements with star, we say we consider nothing. Or you can say the block is trivial one element.
You don't allow valid in the lower triangle, only in the upper.
But why you say low? I mean,
Okay, you're
it doesn't,
Yeah, I'm just trying to
it
understand.
doesn't matter
Everything,
if take up or low, but I'm used to write zero under diagonal. And
so everything will now be upper triangle.
yeah, all matrices I try to go upper triangle, right? And so our first result really reduces everything for 2 by 2 matrices. And then we are in 2 by 2 matrix situation. Now there are two cases. Characteristic of our field could be positive or zero, right? So in positive characteristic, we obtain complete discrete characterization, Liouville or not. And so maybe I don't have much time to speak to write, but I just say, so in characteristic P, everything is reduced to the Krull dimension of the corresponding group. So reef products, for example, are basic examples where we see trivial, non-trivial. For example, we take the reef product with ZPZ. The dimension, Krull dimension would be equal to D. So in reef products, one was very good. In some other classes, of course, one was good. When dimension was 1 or 2, we had trivial. If greater than 3, then non-trivial. So in characteristic P, we prove the same thing in general. So only if Krull dimension is greater than 3, then always non-Liouville. If Krull dimension is 1 or 2, then Liouville. So even for this Krull dimension 1, it recovers some linear groups classes considered before. But now it's true in general. And now, but the question remains open in characteristic 0. Yes.
So I think the result is that the big thing has no bounded harmonic functions if and only if all of the little things have no bounded harmonic functions. That's the result.
Yes, this is the result. But then in trivial path, really understand 2 by 2. So even for characteristic P, it seems to be very new, but at least here we are done and to understand what happens. But we want to understand in characteristic 0. In characteristic 0, we have some partial results, but we still something very essential to us to understand to understand the characterization is the following thing. So I want to mention this question. About our space polynomial property. We really strongly believe that the following question about polynomials should have a positive answer, but we don't know how to prove it. And if the answer is positive, it would be give a complete characterization for a linear group when it admits a finitely supported measure is not trivial boundary. And I explain the question. So we have a polynomial and several variables.
Integral.
With integer coefficients. We can assume it's a reduced one. And we take another polynomial Q. We want to say, we start this polynomial P. And we want to say, unless there are trivial obstacles, that we always will have the following property. If we take another polynomial Q, a Q we take with coefficients plus minus 1. And wait, first we want to say there exists some constant C, such that whatever other polynomial Q we take, and we take, so what we want to say that Q is not divisible by P. But it can happen that Q is divisible by P, right? But you want to say, if instead of looking on Q, all variables we put to the power of C, we want to say that it is not divisible by P. There are obvious obstacles, right? If you start with, I don't know, x minus 1, and the other polynomial x minus 1, whatever CC you take, xc minus 1 will be divisible by x minus 1. So if a polynomial is cyclotomic, or in our case, we need to say cyclotomic in the sense, if our polynomial P, if it divides the difference of two monomials, then clearly we never can have such property. So we need to assume P is not a divisor of two monomials, x1 to alpha 1, x or alpha n minus x1, beta 1, xn, beta 1. And we want to say we always have this property. We could prove it in some situation. Maybe I don't have time to comment now on the groups. So for some groups, like for example, Baum's-Lax group, so these three products I mentioned, they are finally generated but not finally presented. But there are well-known groups, how you make them finally presented ones. So this property was at the beginning of our understanding some of the groups. For example, for Baum's-Lax groups, we proved that we have this property, just this property for 1 plus x plus y into variables leads to our understanding of the entropy of Baum's-Lax groups, and but in general we really want to understand this. I think I don't have much time, so I mentioned in the title also geometry, not only Poisson boundary for linear groups, but in fact this property is related to many other geometric properties of Reeve product. So last month in Princeton I spoke about isoperimetric profiles. This question is also absolutely essential to understand isoperimetric profiles of linear groups. And maybe just the last general comment that on one hand, linear groups are very classical object. On the other hand, many questions about the asymptotic behavior in geometry remain open. So, for example, Aaron Wright mentioned last week, so nilpotence groups are somehow like abelian. Yes, but not quite, right? Look, just mention one geometric question, what we want to understand. We have two groups, and we want to say geometrically, are they similar or not, right? Even for nilpotent groups here, which are linear groups, right, we don't know. We have two quasi-asymmetric groups, but are they commensurable or not? This is a very famous question which still remains open. Now, turning to exponential growth, also, for the moment, it's absolutely not understood which groups are quasi-symmetric or not. There is some progress in the work of Gournay and Tessera that even for for one-dimensional Reeve products, for example, it was an important result many years ago of Alice Eskin and his collaborator. Now, even for two-dimensional Reeve products that are linear groups, right, now there is understanding in the work of Tessera and Gournay, and one can ask, for example, for these groups I'm thinking about, which are quasi-symmetric or not, but I guess I have to stop here.
Are there some other questions?
You mentioned the Kroll dimension of a group.
Yeah.
Could you say what that is?
Just something basic about metabelian groups, right? It's only about metabelian groups, but I'm speaking 2 by 2, they are metabelian. So metabelian groups, something from the work of Holland, everybody, everything is like this. So we have an extension of something abelian by something abelian, right? When you can consider your subgroup as a module, so it's a model over Z. So here you have a finitely generated quotient, let's say ZD, right? We can consider our subgroup as a model over ZD. For us, it's more natural to consider over a field, or closer to the right definition dimension of instead of field, you take a set, right? So we consider subgroup as a module, and you just consider the usual Krull dimension, right? So for a module, it's the same. So just you have this ring, you mod up by annihilator, right? And just the Krull dimension is just the chain of maximum chain of ideals, right? And so for metabelian groups, it was very much studied by Tushnev and by Jacoboni. So, but even in metabelian case, so it seems to be very new, right? So at least in characteristic P, yes, in characteristic P, it's really our result is say it's really defined by the Krull dimension. And in characteristic 0, we have a conjecture. So actually, we prove if dimension is greater than 3, then we prove the boundary is non-trivial. If dimension is at most 1, or some examples even dimension 1 are new, or if it's 2 in characteristic P, we prove it's trivial. So the only difficult case if dimension is exactly 2. And here we have a conjecture, and it's really important to look on the blocks I defined. So in dimension 2, so if the block is a Reeve product, then the boundary could be trivial. But if it's not, our conjecture, it's always non-trivial. And this polynomial question, we will confirm it. So far we understand this polynomial question, we will understand what happens with blocks and their dimension, but we don't understand this.
So this polynomial question, I think you pointed out to me that maybe Lent and some proved that if the zero set in this, they call it atoroidal, right?
In a total case.
So that
Thank you
means
very much. Absolutely had to say. So this question, we asked it in around the same time, Klaus Schmidt and Doug Lind asked
Yeah.
the same question. And in fact, this property, even a bit stronger one, so Klaus and Doug, they were interested not only in such spacing finite, where everything is periodic, they considered just sum of monomials such that the difference with different monomials is big enough. So, and for a total case, they prove it in general.
Total, I'm just trying to remember, that means that the zero set intersect the product of the circles is lower dimensional, is that correct? And then they can use some analysis on the boundary.
Yes, maybe
They prove it's true.
I'm not ready to comment this, but they prove so in some. So our class of polynomials considered was less general than the general total case, and we have very different proofs. So our proof is really more algebraic, and their proof is really dynamical, for our formulation, really maybe it's good to think a bit more algebraically because we really need only its algebraic settings. So yes, I have not mentioned why I spoke about entropy. All these proofs is by estimating entropy. So just understanding this property helps us to give a lower bound for the entropy, and so we just find very explicitly some polynomials. For example, 1 plus x plus y, we can take c equal to 3. So this gives very explicit estimate of entropy. So Dark and Klaus results it's less explicit, but both they and we absolutely want to understand the general question and really don't try.
So yeah, what's the fewest number of variables where you don't know? Like, do you know that your question for 2 variables?
No, I think 2 is maybe as difficult as general. For one variable, well, it's pretty trivial. So it's clearly true for if you have one variable. So then it's clearly even only if your polynomial is cyclotomic, then it's very easy to see if it's not a cyclotomic, then you have this property. But for 2 variables, no, we absolutely don't know, and really looking forward to understand better.
Okay, if there aren't any more questions, let's thank Hannah again.